Okay, this chapter will be on generator stator winding protections and how we will apply, how do you protect the stator winding. However, I will give you an overview what type of generator protections are there, and then I will focus on the stator winding protection. So I'll go to types of faults that would occur in a generators, and what are the protection to protect those types of faults. And I'll go then focus on the stator winding protection for phase faults protection and ground fault protection. I'll give you an example. This is a generator stator side. It's connected to the system, and this is the rotor of the generators and fed by through the excitation system. And this is the turbine which drives this rotor or the field, okay, of the synchronous generators. Okay, so we have different elements here involved in our generators. We could have a faults in the stator winding. I could have faults between phase to phase, like 2. I could have turn to turn, like number 1, a turn to turn fault. I could have fault from a winding to ground, to the stator case or core. And there are, so these are the, could have a fault outside, okay, outside the stator winding. So this all the stator winding fault is which is inside, which is involved inside. We have also rotor and excitation faults. We have like also could have a turn-to-turn faults in the rotor winding, or force between the rotor winding or the field winding with the core could be of the state of the rotor. I could also have issues with the excitation system, the DC supply provided to this. I might lose this excitation. I want to detect that I have lost the excitation. Okay, so we have under excitation or over excitation problem. Maybe with exciter can provide higher voltage than what the field winding can handle. I would like to also detect this problem. There is also something wrong with the prime mover. I want to see if the gas turbine or steam turbine has a problem. Some of the problems, like the under or over frequency, as if the speed goes high or low, have also to protect the turbines, okay, from being damaged also by detecting the frequency, the speed, okay. There are other also mechanical protection like vibrations and all, so many other protection. I'm just looking at the electrical part, okay. Reverse power. If you lose the turbine, power will be taken from the system and try to drive this synchronous machine. So instead of supplying power, it will now absorb, consume power. And I want to see if the power has reversed or not, as indication of a loss of the turbine. I can also stick why, the valves of the turbine shut down directly. But I don't have a signal from here goes to the relay. Rather, I can detect this by measuring the reverse power. There's also possibilities of outside force in the network that feeds. This is a feeders goes from the main bus bar at which this machine is connected to. If there is a fault here, okay, I will also detect those faults, such as short circuit, or there is also ambulance conditions that can occur. Okay, suddenly loss of this feeder. Okay, so the machine will be under loss of load, we call it, or sometimes the machine is off and suddenly you close the breaker without synchronization. And as a result, you want also to detect this this conditions, or sometimes breaker failure. You want to close and it's not closed. So we want also detect this. So many faults and abnormal condition can occur in the generators, okay, as compared to other devices. As a result, I would need different types of protections as shown in this slide. For a stator and phase and ground fault, I could use differential protection. This is the generator, and this is its transform. This is like the star point of the generator, and this is the a grounding transformer, which is connected to the ground or neutral resistance, grounding neutral resistance. And so instead of measuring the current that will pass through the neutral, I can measure now the voltage across this resistance as indication of a fault in the resistance. So this is like 59G instead of 51N. We can also detect, this is also, this will I will cover this inshallah also. Not the 51N, we'll put here a CT that measure. Instead, I'll show you the grounding. How do we ground generator winding? So we can use also 51 here, just CT here in the neutral, and to detect ground faults. I can also detect the ground fault in the stator winding by the differential relay. The differential relay, which is a relay that requires 2 CT. So the stator winding, this is the stator winding. I have 1 CT here and another CT this side. So I have 1 CT and another, sorry, that's not this one, this one, with this one. These are 2 CTs, like 3 CT, I think, 1 for each phase. And then it's connected to the differential. This is the generator differential. We call it 87G. G represents generator. So that detects the faults in the generator's stator winding. Also detects not only phase faults, phase-to-phase faults, which is phase-to-phase faults, also phase-to-ground faults in the generators can be also detected by the differential relay. So this provides phase faults and ground fault stator winding protection. The transformer, normally generators are connected to the system through a transformer, which steps the voltage from 11 kV to, let's say, 220 kV or 66 kV to the level of voltage by using this step-up transformer. And this is the breaker, main breaker at which I would like to use it to synchronize this machine to the system. So this transformer can be also protected by differential relay, which is 87T. CT is here and CT here. And this transformer is delta, okay, delta on this side and star on this side, okay, and that's why star is grounded. So delta this side, star on the other side, as you can see here, and the star side, which is this side, is grounded. So I need an overcurrent ground fault protection. So CT in the ground high. And to protect the windings here, I have, as I mentioned before, the star side is delta connected CT, and the delta side is star connected CT. And these are going to the, as a differential relay, 87T for the stator, for the transformer protection. And I have also a transformer that feed the utilities, the auxiliaries of the generator. I have so many auxiliaries required for this. like for the pumps and cooling systems, oil systems, all need power, and this fed from the unit, we call it sometimes unit transformer, generator unit transformers. And this also has a differential protection, as you can see here. There is one differential protection is called 87O. O represent overall generator and transformer protection. And that CTs are connected here at the beginning of the stator winding, before the star point, the stator winding, beginning of the stator winding, and end of the secondary side of the generator transformer, and also another here. So any fault within this region will be detected by this by this differential relay. We call it overall differential relay. And we have, this is the field breaker, that field winding. Also I have protection that detects, let's say, loss of field, okay, or ground faults in the field winding. We have also, like, if I want to see synchronize this breaker, or I say this breaker failures, or okay, there are other protections, like I need a VT here. This is like a VT and a VT, and we have some like from the VT I can measure the frequency of that voltage, and from which I can say this is over or under frequency, or under and over frequency protection. I have loss of synchronism, okay, as the still this are in phase or in synchronous. We call it also ball slip protection, loss of field protection, okay. We have reverse power, and reverse will require two things, you know. We need a current, which is this fed from this CT, okay. So we have a current, and I need also a voltage which comes from this VT, sorry, from this this VTS. So it requires both things. Current, which is, sorry, current will be from this side, because I would like to measure this current or reverse current, and the voltage is this, from which I can measure if the power has reversed or not. And there is V over H, V over F. So V divided by F, voltage per frequency, because the volt per hertz. And this is, I need the voltage and frequencies enough to know the voltage here signal, I know its frequency, I know, so the voltage magnitude. As a result, I can check the ratio, and this ratio represents the if there is an overfluxing, core saturation of the generators. And so there are so many protection. My focus will be on the differential, okay, relay protection, and for the stator winding, and also I'd like to compare it with the ground protections for faults in the stator winding, and especially for faults close to the star point. This is the star point here, close to the star point. And this shows you different types of protection. As I said, we have stator winding protection, winding faults. We have rotor winding protection functions. We have some protection functions to detect abnormal conditions, like reverse power due to loss of the prime mover, negative sequence due to imbalance. Maybe one of the generator breaker did not close, so you will have imbalance in the currents. So you can detect it through measuring the negative sequence current. Under excitation due to loss of the prime mover, excitation failure, sometimes a fuse can blow. Okay. Circuit breaker inadvertent energization. You close a breaker before you get synchronized, the system synchronized maybe, or the generator is still dead, it's not working, and you close the breaker. Breaker failure, abnormal frequency, over or under, loss of signal. So many protection failures that you need different types of protection functions in order to detect all these types of faults effectively and accurately. Now, what I want to focus on this chapter, after this introduction, on this is the star point, okay, the star point, which is this point now. This is abbreviated with this. And from the star point, I'm taking it out to a neutral resistance. We call it sometimes NGR. Maybe if you go to work, neutral grounding resistance, okay, which is RN in this case, okay, and that goes to ground. Okay, so we in single line diagram, we just show it as this. This is the star point, and from star point I get. So what I want to do, I compare the differential relay, a CT at the stator winding. This is the two sets of CT. This is single line diagram. So this is CT number 1, set of CTs. This is CT2. Okay, and these are the generator 3 windings, stator windings. So this is the differential relay, the 87 G in this case. Okay, so this characteristic of differential relays, we will use a biased differential relay, and I want to compare the currents at this side. I'll call this I1, and current at the other side that goes to the relay, we'll call it I2. Okay. So each phase will have the same thing, okay, except I will just focus here, single line diagram, they will just draw it in this way. And this is, or they will put the differential like this instead of putting it here. So 87 G, as I showed you in the single line diagram here, right? 87 G. And this is the CT that protect to detect faults to ground in the generator winding. So I'll compare these two when they have a ground fault. So when I have a ground fault in the, this is a ground fault now. Okay, one phase is to ground faults. I want to see how this differential relay works as compared to the relay, as compared to overcurrent. And when this fault is very close to the star points, this close somewhere here, this is, we'll see how the sensitivities of these two types of protections. Normally, differential relay, we used it for when you have a generator of more than 1 MVA and or big motors of 1,500 HPs. Justify the cost of having a differential relay. CT1 and CT2 has to be in the same ratio because the current in is same as current out. So not like a transformer where primary is different than secondary. So the current here is same under normal operating conditions. Bias differential settings, the slope, we choose it as 5 to 10%. And the minimum pickup setting of the this one IS is 5 to 10% of the nominal rated secondary current, which is 5 or 1. 10% of 1 or 10% of 5 ampere. Now, to see why do we need, if this provide a differential, provide both rotor and ground fault and phase fault protection, why do we need here? Okay, and why do we need a ground fault protection from the first place? Okay, oh, sorry. Why do we need to grounding resistance from the first? Why we don't solidly grounded without ground? So this is used to limit the ground fault current. So why do we need to limit the ground fault currents? Because the core of the stator can get damaged quickly at low current. Okay. And this shows you the graph of the current magnitude versus time that the stator core can handle. Okay, so this curve, this one, okay, this curve, if you work somewhere here, which is the right side or above this curve, that will lead to damage of the core, severe damage in the core winding. So when you work on this side of the curve, it is negligible arc damage. So it is a safe, even if you have a fault, it will not damage the, when you work somewhere, anywhere here. So you will have no issue, no damage on the core. So as a result, as you can see, at 20 ampere, right? Or let's say a 40 ampere for a duration of 10 seconds can damage the core of the stator. 80 ampere for roughly 1 second can damage the core, yes. Any questions? Okay. So what we want to do here, we want to limit the fault current in the ground current in the core, so that the ground current roughly less than 20 ampere. Okay, maybe 10 ampere is good, so I can stay longer time before the stator winding get damaged, the stator core get damaged. So I will limit the current to 10 ampere. Although they may be generator winding, rated current may be 1000 ampere. Okay. However, for ground fault, I want to limit that current to 10 ampere. As a result, we use different grounding resistance, high impedance grounding, okay, resistance, okay, to limit that fault, ground fault currents, okay. So this is the different grounding systems. Here the stator winding grounded directly through high resistance of 1 kilo ohm. This is neutral grounding resistance. This is practice in United in Europe. While in US they use grounding transformer. Grounding transformer then connected through a resistance of small, because at the end, if you take this 0.5, I'd have a ratio of, let's say, 100, to 1 ratio. This will be 0.5 times 100 square over 1. Okay, so like I'll have 5K ohm in this case. If I have a ratio 100 to 1, 10, I would, so this is like equivalent to this. So this is the practice in USA. So both are this is high impedance or high resistance grounding systems. We could have also low resistance grounding. Low resistance normally used for small generators or industrial generator, and maybe in one of the plants, small plants, our standby generators or diesel engines, we could also directly ground it through a small resistance, or solidly grounded. We could say solidly grounded is directly connected to ground instead of through a resistance. We have something called isolated grounded system, where this is not connected to the ground. So in case of a fault, ground fault, there is no ground fault. And there has to be a system where you should detect those types of faults before another ground fault occurs. So my practice here, just I want to focus on these types of grounding system. Now, in case of ground fault, this is the stator winding. This is the winding 1, winding 2, winding 3, 3 phases connected as a star, and then grounded through a resistance. This is the voltage of each phase A, phase B, phase C. Okay. And now if a fault happen to ground, so this is the ground. So if the fault at the end of the stator winding, the voltage will be at the stator winding is full voltage, rated voltage, which is 100% of rated voltage. When a fault at the star point, the voltage is 0. That is produced from the generators because fully grounded. Now the voltage at point X, at point this voltage, and suppose this is X per unit from the star point. So, and we'll say 1 per unit of the full winding. So at this, or urban percentage, this is X percentage of the winding is faulty. So the voltage that will be here will be E at point X. And that voltage will be X times the rated voltage of one phase, which is E. Okay. E represents the phase voltage, the voltage from this to neutral. Rated voltage of the machine normally is 11 kV over root 3. The rated voltage of line to line 11 kV. So that's represent EX, okay, the voltage from here to here, to the star point, EX. So that's EX, the voltage from the star point to the fault point. And X represent the fault percentage of the winding which is faulty in per unit or in percentage, divided by the resistance and the impedance of this portion of the winding. This portion, the impedance is R plus J of the stator, JXZ, direct axis or synchronous reactance of the stator winding. Now this is full. If you have a percentage of the fault at, let's say, at point X, this will be also as a percentage will be R times this. I'm neglecting the armature. This is the armature. I'm neglecting the armature resistance. Armature resistance very small as compared to the reactance. So we neglected this. We have just this one. So this one times X, because I have a portion of this faulty, plus the neutral resistance. Okay, that's going to be the voltage from here to ground. Okay, this is EX is the voltage from here to ground. So that's not here. This is EX from here, from this point to ground. So that voltage is to here. So if you divide this voltage over the impedance of this plus this, it gives me the total impedance to the fault point. And because as X becomes closer to the star point, this becomes negligible. this part. And then we'll have just root of Rn squared, which is Rn. So approximately I can uh, uh, estimate the fault current in the neutral, okay, or the resistance by using EXE over Rn, okay, and from which I can design, if I want to find my fault current to be limited to 10 ampere, 10 ampere, I have to use, let's say, rated voltage divided by resistance. That give me, this is when you want to design the value of this. I would use not X times E, I would do the phase voltage divided by Rn. That gives me 10 ampere limited current in the ground. Okay. Now I want to compare these two scenarios. Now, if I have two type protection, one protection as a differential, another as ground force. As a ground force, I have a CT here that's connected to the overcurrent. So this is the 51 G, 51N, or 51N, I'll call it 51 N. 51N. Okay, this is the to detect ground force. So there's a current here. I'll see a current in the secondary, and this can, if this current get it and then pick up, I will detect this one. Or I can have a differential. Differential really, I have a CT this side and a CT this side for each phase, right? Then I'll connect them to, okay, to a differential relay. Okay, so I want to see now this CT. I'll call this for the differential for the overcurrent relay. I'll call this CT. This one, CT of the neutral. I'll call this one, and this is CT2. In this case, same as this CT2, because this is same ratio. Okay. So CT1 now, what will be the current? This current, let's call this I setting of this both. So for differential, I'm assuming this is the minimum pickup setting, I differential versus I restrain, and my setting also IS. So we'll choose, for fair comparison, I'll choose my minimum pickup in the differential relay setting for this 87. This is 87 G, or okay. I'm just drawing one phase, okay? These three phases. And this is, I would like to, so I'm selecting the pickup setting of this 51N and the 87G minimum are same, so for fair comparison. So what will be the current in the fold? Current, as we found it, the current here, which is when you have line to ground force, I have a current here, okay? And also I'm assuming now these are not connected at this side, so the current here is 0. So that current will be reflected here, go to the differential relay. Okay, so dividing this current, which is I fault, okay, divided by CT ratio 2, give me this current, and I would like to see, is this current greater than IS? So that current is, the I fault will be XE phase divided by Rn, that gives me the fault current. If you divide by CT ratio 1, give me the current, this I relay side. I the current. IR here is not the restraint. What I mean, I will call this, let's say, IR capital, so that you don't confuse between this IR. This is the restraint current. This is IR capital, relay side, or I call this I51. Okay, so this is the current, this is the fault current that goes to the relay. If this fault current greater than the settings of this relay operates. From which I can find that X unknown is equal to IS times this divided by. So this is the first relationship I would like to see. Now this settings I know, the setting, let's say, of the overcurrent relay, then I'll see what is the minimum value of X that will be detected by this overcurrent relay. So the smaller X is the better, okay? Because that will give us, you know, the portion that will not be, if this becomes 0, okay, means, you know, if this becomes 100%, you know, I want to minimize this one. This is the portion of the winding that will not be protected. So I want to minimize it. The second, when you have differential, it's the same thing. I thought, which is same divided by CT2. It gives me this current and this current. Now I'm assuming this is open, so I'm assuming this current is I, because breaker is open. I'm assuming, so this current is I equal to 0 from this side. So there's the differential current here is the difference between this and this 0 will be like same as this over CT2. So that's also, this is the fault current divided by CT ratio 2. This gives me the fault current minus I2 give me the differential current, and I2 here is 0, and that also has to be greater than this. This is the first condition, and sorry. And as a result, from this relationship, we can find also X, and that will be, if you compare these two relationship 1 and 2, okay, we compare these two, which one is more sensitive? I won't say sensitive, which one would provide larger percentage of the stator winding that will be protected? Which one will minimize? Which X is smaller? The smaller X, the better. Okay. So if you compare, okay, the differential CT will use for this CT. Normally, the ratio of this CT will choose them based on nominal rated current of the generator, and this is in 1,000. Maybe generator rated current is 1,000 ampere. I'll choose 1,000 to 5. While the neutral grounding is not chosen based on full load current here. You will choose this one, or because the current here normally is 0 during normal operating conditions. So we don't choose the CT, and because this will limit the current to, let's say, 10 ampere, I can go to 50 to 1 or 50 to 5 ratio. So the ratio of CT1 is much, much smaller than CT ratio that is used for the differential relay. As a result, so because this CT1 much, much smaller than this, as a result, this quantity becomes smaller than this. As a result, X for the overcurrent relay becomes smaller than this. So as now this becomes the 51 more sensitive than the differential relay in detecting ground force close to the star point. Let's take an example to show you this. By this example, I have grounding resistance 25 ohm, an overcurrent relay with a CT in the neutral of 200 to 5 volt at point X, which I don't know, want to see. What is the percentage? Sorry, I want to, let's say, I have the rating of the transformer, its reactance, which is XD, or XS in this case. Compare the neutral grounded throw 25 ohm. This is this ratio, and determine the pickup current. Yeah, I want to find the pickup current. Okay, in order to achieve 90% protection of the stator winding, I want to protect 90%. So what does that? I want to protect up to here, up to 90% of this winding will be protected, means will be detected by this. So I will left with the remaining 10%, which is will not be detected by this. The remaining 10% unprotected portion, unprotected. And this is X, our unprotected. So this is our X. X here is 10%. So X is 100% minus the protected portion is give me, this is X, which is 0.1. Now the voltage at up to X point, okay, the voltage here up to 10% will be 10% of the rated voltage. Rated voltage is 11 kV, and this is line to line. Over root 3 give me the phase. So this is E phase. Okay, and I take 10% of that, give me the voltage EX. So this is the voltage EX. From that point to ground, okay, I'm assuming. The generator reactance is because I have 10% only of the winding, and this is left, so you have 10% of the reactance, which is 10% of 0.2. Okay, I'll just convert it to ohm by multiplying by Z base, which is V base square over S base. This is Z base times 0.2, I convert it to ohm. This is the reactance of the full winding. And now I take 10% of that, okay, plus Rn under root square, which is same as this formula, okay, as this, to find the fault current. So it gives 25 ampere. This is even now. If we neglected this, we'll get almost same. You know, if I neglected this portion, we'll get almost same. So sometimes we may also neglect this, especially if the fault very close to the star point. And the fault current at the relay side, what will be this current now? The relay side, this is not the restraint. Relay side current is equal to that fault current divided by the CT ratio. So 25 divided by the CT ratio of 205, I get 0.64 ampere. So this is, I will choose now a pickup setting is equal to 0.64 in order to protect 90% of the stator winding. If I choose higher than this, I will not be able to achieve 90%. I will get less than 90%, which is okay. But why don't we go smaller than this so that I protect more than 90%? The problem that I cannot go lower than certain value of normal current in the neutral during normal operating conditions. I have neutral current here during normal operating conditions, normal imbalance currents. Okay, uh, maybe third harmonic currents are also regarded as a neutral current. So that I should see what will be the neutral current during normal. Maybe if it is, let's say, 0.3 ampere, I cannot go below than 0.3 ampere. Okay, my setting. Otherwise, relay will trip during normal neutral current that flows in the neutral. And now this example, I would like to illustrate the comparison now between this and differential relay. Now, in this example too, I have a differential relay uh, and two CT, a system, a generator connected to uh, um, through a transformer to the system through a circuit breakers. And I want to see if a fault at F1 and F2, uh, how the differential relay will operate for F1 and F2 faults. So a generator connected to infinite bus, this is the infinite bus, by a delta star transformer. The generator winding are protected by a differential relay. The system data are given. This is generator ratings, transformer ratings, the infinite bus fault level. Okay, this is the fault level, short circuit, the rated voltage and system reactance. Okay, and I have also given the settings of the differential relay. This is bias, which is K constant, and the pickup setting, which is IS. Okay. When the generator is not connected to the system, in circuit breaker is open, calculate the fault current for a solid three-phase fault at F1 and F2. So I will define what fault currents here. Determine if the differential relay will operate for each of these fault locations. Repeat A and B when the generator is synchronized to the system, when this is closed. Now, the generator rated current, to know the CT ratio is not given to me, so I will choose the CT1 and CT2 ratio first. Okay, so I need to know the rated current also. So the rated current is the MVA rating of the generator over √3 line-to-line voltage. I got the rated current. So I selected a CT ratio of 5,000 to 1. As you can see, this generator stator winding current 4,600. Okay, but when I have a ground fault, I want to limit it to, let's say, a small current of 20 ampere, 10 to 20 ampere. And that's why I need high grounding resistance. Fault current for a three-phase faults at the generator terminals will be when you have a three-phase faults here at the generator terminals. How do you get that? The rated voltage divided by the reactance of the stator. The reactance of the stator winding is this. So it's just Ohm's law. Okay, if you have three-phase faults here, I want this voltage divided by reactance. Now I'm neglecting the resistance, as I mentioned here. We neglected the resistance. So that voltage, phase voltage divided by the resistance of the reactance of this winding give me the current, fault current. And and that's if I use phase voltage, rated voltage divided by reactance, give me the fault current. Or I can also find by using the per unit voltage divided by reactance of the stator. It gives me also the fault current in per unit times I base gives me the current in ampere. So I fault, because line to line voltage is 15 kV over, I can do it also the same thing. I 15 kV over √3 divided by, this is an ohm, to give you the fault current, or you convert this to per unit divided by the per unit. So 15, if I'm using 15 kV as my base, this will becomes 1 per unit divided by per unit, give me I fault in per unit. Okay, times I base gives me the fault current, which is I base already the rated current of the generators. So I got the current at the fault current. So 1 over 0.2 to represent 5 per unit. The fault means 5 times the rated current. Fault current refer to the secondary side of the CT. Now if I take this current and refer it to secondary side of the CT, because CT ratio already 5,000 to 5, so I got this is the current referred to the secondary side of the CTs. Now for fault at F2, which is this one, fault, I'm now assuming the breaker is open. So when the breaker open, okay, so the fault current will comes to this fault like this. So there will be a current in CT1 and CT2, but when the fault is here, there will be no current goes into CT2 because the breaker is open. So it's only CT1 that has a fault. When they have fault 1, will be here. So there will be no current going to CT2. So for fault 2, I1 secondary and I2 secondary same, which is I fault divided by CT ratio, which is this one. And then the differential relay difference between this is 0, and relay will not operate, and this is correct action because fault after the 2 CTs. When a fault's either here or anywhere beyond the 2 CTs, the differential relay should not operate because it's out of zone faults. For F1, the current I1 will be same as fault current referred to secondary side, and I2 becomes 0 because there will be no fault current passing through CT2. So I2 0, and differential current is this, and restraint current, the average of these two currents, and I'll check the relationship. Is ID greater than IS? I differential now is 0.23, greater of course than IS. IS was 0.2, so this is greater than 0.2. Okay, so this first condition satisfies. Is it greater than KIR? A K is 10%, 10%, and IR is this. 10% of this becomes 1.1. So ID greater than 1.1 also. So both conditions satisfied, and as a result, relay will operate. And this is also a correct action because faults between the 2 CTs. For when the breaker is closed, this is a closed condition. Now, I have a fault also coming from the systems feeding F1 or F2. Okay. This is I fault, but comes from the system side. This fault is coming from the generator side, a fault from the generator side, feeding this fault. So the equivalent circuit and per unit of this, so I have a reactance that represents stator winding, a reactance that represents the transformer, and the reactance represent the system. So this is the generator winding, the transformer reactance in per unit, and system reactance in per unit, and this is the system voltage and the generator voltage. So we normally operate at 1 per unit, so I'm assuming the system as 1 per unit voltage, which is at rated voltage operating. This means at 15.5 kV at this side, and this side will be 345 kb, so this becomes 1 period, this also becomes 1 period. Now for a fault at F1, F1 represents an end of the winding, of the generator winding. So it's somewhere, this is the end of the generator winding, so this is a short three-phase fault here. So there will be current fed from the system, current from the generators, that gives you I faults. But the CTs, CC could be here or here, depends on the F1 or F2. Okay. So now to analyze this, I need to represent the reactances as per one base. Okay, so I have to unify the base value. So I choose 100 MVA as a base, 15.3 kV as a base at the generator side. So in this case, this will be same. The generator rating is 125. Because I use 100 MVA as my base, this has to be changed, to the new value by base change. So this is just from power systems 1. So 0.2 times 100, 125. I converted to base, the value of the generator winding to the new base, and transformer also, because transformer is 15.5 to 345. 150, which is different than 100 MVA base, so I will also need to change 15.15, okay, which is the generator so the transformer reactance according to its rating to the new base. I got this one, and the system already this per unit already based on this power and this voltage, so there will be no change for this value. So that system will become same as, and as a result, now we can find the fault current. So what will the fault current? Okay, I can take the fault current this plus fault current this, gives me the fault current. So what's fault current? This is 1 divided by this, okay, and fault current from the system is this one, system voltage over the sum of these two, give me this. If you add these two, give me I faults, okay. This is fine. I want to find I faults, but I'm okay. So, and then we can multiply it by I base to find actual fault current. So I base, based on this values, is 100 MVA over √3, and the base at the generator side is 15.5. I got the base current at the generator side, and then I can find 1 divided by this impedance. It gives me times the I base to give me the actual fault current IFG, and similarly I'll do for I fault at the system, and we add them to get total fault current here. So what current that will pass through these two CTs is not the total fault current, only fault current that comes from the generator side or from the system side, depends on the fault. The fault at F1, the fault current that passes through CT1 that goes from the generators, and the current that passes through CT2 is coming from the system, okay? So I need to know these two values, this and this. This value can be also obtained by taking the Thevenin of the Thevenin equivalent circuit at the fault point here. If you take the fault, remove this fault and take this Thevenin impedance, we'll see this is in parallel with this. This is Z Thevenin. Then if you divide V Thevenin will be also 1 per unit. Then if you divide V Thevenin over Z Thevenin, give you the fault current directly. Okay, this is another way to find define this one, from what you multiply by I base, I get this one. Okay. Now, for each case now, our scenario for fault at F2, for fault at F2, fault at the end of the after the CT. So this corresponds to here. So the current coming from the system is 29,800, and the current from the CTs from the generator side 23,800 something. This is from the generator side. I fault IFG. Okay, and that's IF system. And now fault is here after this CT. So there will be no current. The current in CT1 and CT2 is same as this. Okay. As a result, the current in the secondary side of CT, this CT1 will be, this is I1, and current in CT2 is this current also divided by this CT ratio, which is also, this is I2. Okay, and now if you take the differential current, okay, so this is the current here. If you take the differential current will be 0. As a result, relay will not operate, and this is correct because this is outside. So there will be 0 current flows in the differential relay. And in case of fault at F2, sorry, F1 here, I have a fault current comes in CT2 due to I system, fault system. But CT1 is, so that's the fault inside. So I have current here is fault system. But the CT will have I fault from the generator side. Okay, so these feeding the faults. So in this case, if I divide this divided by CT ratio, I get this. If I divide this over this CT ratio, I get this. However, the current now has reverse. Now the current leaving this dot correspond current entering the dot. So this is the polarity. Now current leaving this dot correspond to current entering the dot. So the current is in this direction. Okay. So sorry, in the other direction. It's not this. It should be leaving the dots, means leaving. This is leaving. This is entering. It should be in this direction. So this should be here. That's why it's just in this direction. Now, if you compare the two, this is in and this is out. So the differential current 0. While here, the current will reverse. Now, current entering a dot correspond current leaving a dot. This is in this direction, right? And this is current leaving a dot correspond current entering the dot in the secondary side, so current in this direction. Now, if I compare this phase with the same phase in the other side, which is this phase, so both currents are now N to the relay. So this differential current becomes summation. So this will be added, this current will add it with this and give me this current. Okay, and now this is in case of fault at F1. So I1 is same, I2 will be now to a reverse direction, right? I2 is reverses direction, so I put here a negative, and now the differential current becomes added instead of subtracting. And now the restraint is the average of these two, the average of the magnitude of I1 and I2 magnitude over 2. I got this. Now I'll check the condition. Is ID greater than IS? Yeah, ID already greater than IS, which is 0.2. And as ID greater than KIR, K, which is 10%, and IR of this 226 will be 2.66. So ID also greater than this, so both conditions satisfy, relay will operate, and this is a correct. So this is that's when we have only differential protection. And now what I will compare, if I have this is grounded through resistance, and I will also compare the operation of this as compared to the differential relay. This is the last part of the example. And I will also compare it. Now in this case, I want to analyze the operation of the overcurrent relay with the differential relay when both have a minimum pickup setting of 0.2 ampere. This is the pickup setting, I settings of this, same I setting of the overcurrent relay, same as the minimum setting of the differential relay. And let's see which one would work better for different values of Rn for a fault at the end of the transformer winding. And I will assume now the breaker is open in this case. Okay, so we'll do the same thing. First, for line to ground faults, we want me to compare the operation differential relay and the 51 relay. I want to compare the operation of these two for line to ground faults. So for line to ground faults here, I need to draw the positive and negative and zero sequence of this system networks, and then I'll connect them in series. So this is the generator reactance, this is the transformer reactance, this is the system reactance, this is the positive sequence that we draw it for face-to-face fault analysis. And this is the circuit breaker location, which is this one. I just put it as a switch, okay? And the negative sequence will be same as positive without sources, okay? But the reactance is here. This is now positive sequence reactance of the generator, positive sequence reactance of the transformer, positive sequence reactance of the system. Instead of positive sequence, it was negative. Normally, negative sequence impedance of the transformer same as the positive sequence. Similarly for the system. However, for the generator, the negative sequence is different than the positive sequence. And zero sequence impedance of the generator is normally also lower than the positive or negative sequence impedance. However, for the transformers and the system, also you have we need to know the negative sequence impedances. So this is the negative sequence network without sources, same as positive without sources. The zero sequence network, you need to include the grounding resistance in the, suppose now here this is solidly grounded. This is solidly grounded in the transformer. But the generator is grounded through a resistance. So I have to show them in the negative sequence. This is also delta star. So delta star, I have to draw the generator winding from the delta side. This is the delta side, okay? And this is the star side, sorry. The delta side.
Victor, there are another lecture.
Yes.
Can I leave?
Yeah, you can leave. I will. I have just 5 minutes to complete this example.
Perfect.
I will. Okay.
Thank you. Thank you, Victor.
You're welcome. So, so this is the star side, okay, of the generator winding, and this is the delta side. Now, how do you connect this? This is the how you represent, okay, how you represent transformer in the negative sequence when it is star delta connected. Now, star side, sorry, I'm always drawing it. Star side and the other side. This is the star side of and this is the delta side. Delta side is open. the star side, because it is grounded, we connect it to ground. Now, if this has a resistance, I'll put it also here. If this is grounded through a resistance, Rn, I will put it also in this place. If I have a resistance, but because it's solidly grounded, I put it here. This is all what I do here is just from Power Systems 1, fault analysis, okay? Or Power Systems 2. In Power Systems 2, yeah, you cover this fault analysis. And now the generator winding is grounded through a resistance of Rn. We put always 3 times this in the in series with the reactance of the generators, and a system, and we connect these 3 networks together in series to analyze line to ground faults. Okay, we connect them in series. So you connect them series at the fault point. Whereas the fault point is here at the end of the generator winding. So this is the end. This is the generator winding reactance. This is the end of it before the transformer. So you connect these, all of them at this point in series. So they connect them in series, and you connect sometimes a series resistance of RF. This is the fault. If the fault is through a resistance RF, okay, means if you have, this is the 3 lines, and if I have a fault with a resistance, this is RF now. This 3-phase faults, okay, with fault resistance, okay, or line to ground faults. Now, if you have line to ground faults with fault resistance, okay. Now I'm talking about line to ground faults. If this is, I'm not including this in this scenario. If I have fault resistance, I'll put it here RF, which represent this resistance of each fault. This is 3-phase fault, okay, 3-phase fault, and this is line to ground fault, okay, through a resistance. So I'll put 3 times also this in the here. So that's the equivalent circuit. Now for the breaker, now this has to be based on the same per unit base, these per unit values. Now if the breaker is open, there will be no current coming from the system. So I'll also note this fault current here is positive sequence. This is negative sequence current of the generator. This is negative sequence, 0 sequence current of the generator. And this is also from the system, and this is from the in the fault point. So that's correspond to, we have 3-phase, this correspond to IF. So IF from the positive sequence is network is this. IF from the negative sequence network is this. IF from the 0 sequence network is this. And all of these are same, okay? In case of line to ground faults, positive sequence current and negative sequence current and 0 sequence current, the fault is same. So when this breaker is open, this becomes 0. I don't have to analyze this portion, okay? So I'll just look onto this part. So IFG 1 and IFG 2 and IFG 0 are equal, okay? Because that current will be here, same as this current. So there will be, now I'm assuming RF, in this case, our scenario RF equal to 0. I didn't consider fault resistance. I have only Rn. So I want to consider Rn, how Rn affects the fault current. And okay, so the solution of this already, the solution of this in your in the Dropbox in chapter 6, I say example solution. So this is when you see open that, this is example solution, okay? And this is the network. As I can see, I'm opening here, so there's no need to draw all of this part because there's no current flow from the systems. Okay, it's like an open circuit here, so I'll just draw the generator side. So this is the generator, 1 per unit. There's positive sequence reactance, negative sequence reactance, zero sequence reactance. I didn't take the a common base of 100 MVA because the other system components are removed. These components are removed, so I don't have to unify the base. You need to unify the base if this is closed, so they have generator and system reactances will be involved. Now, because these are not involved, I have the generator, I don't have to convert the base quantities. So I use same as the generator reactances given in the problem. In the problem, the positive sequence and negative sequence of the generator are same. And this is the zero sequence reactance of the generator. For the transformer, I don't need it because I am not taking it into consideration when the circuit breaker is open. So in this case, so I just am drawing. This is the system, and this is the for line to ground fault at F. This is the circuit. So to find the fault current, this is the positive sequence current from the generator, negative sequence current, and zero sequence current. Now they are same, and their value is equal to voltage of the generator, which is 1 per unit divided by series of these impedances, plus 3Rn. You don't forget, this, it is reactance J, and J, because this is a common mistake that I've seen it in the previous test. Okay, student that this is a reactance, so it has to be with J and 3N. And this is now the positive and negative and zero sequence currents. Once I know this, I can now find the ground fault current, which is 3 times I0. Okay, this is the ground current, or it is I1 plus I2 plus I0, which is 3I0, because they are equal, so 3I0. This is now the fault current, which is coming from the generator, right? This is I fault coming from the generators in case of line to ground faults. And now I'll just consider now for 3 scenarios when the neutral resistance is solidly grounded, or low resistance grounding, and larger resistance grounding. We'll see how this operation as compared to this. Okay, and I'm using these characteristics. I have a pickup settings of minimum pickup setting of 0.2, and the bias is 10%. This is the minimum settings of this is also 0.2, and I'll call the current in the secondary siding is for the that goes to overcurrent is I51N. Okay. And I call this now, because this is open, when a fault here, there will be no current in the CT2, so it's only current goes into CT1, and so I have only I1, I2 becomes 0. So in this case, I know the fault current, and the fault current now, fault current is you divided by CT1, get you this divided by CT of the neutral. Okay, you give me the current that goes to the overcurrent relay. So I find this ICT1, which is the goes to the differential relay. ICT2 of the differential relay is 0 because this is no current from the system. And where is that again? was so here I found the currents, and for solidly to ground faults, we found just this is Rn0. Okay, found the current, then I base, because this is ampere unit, I base is the rated current of the generator. So this is generator voltage over power over the, so I got the current, rated current, which is my base in this case. And if I multiply this by this current, which is the zero sequence, the fault current is this 3 times I naught, 3 times I naught, which was 2.33, sorry, 3 times this, times the base value. So this is the zero, so this is the zero sequence current times the base value. This is an ampere, this is current, multiplied by 3, it gives me the fault current. I got the fault current now at the primary side of the CT of this CT. And this is also the same as here, this current. And so if I divided this current divided by CT ratio that feed the differential relay, the differential relay CT ratio is given in the example. CT ratio was 5,000 to 5. Okay, this is 5,000 to 5. So I divide by 5,000 to 5, which is 5,000 over 5 is 1,000. I get the current at the secondary side of the differential relay CTs. I2 is 0, as I mentioned before, so differential current is this value. The difference between these two, restraint current is the average of these two values over 2. I got the restraint current. Now to check if the relay operate or not, is ID greater than KIR? So I use this characteristics. So a trip condition that ID, what is the trip condition? That relay operate if ID greater than IS plus K times IR. So IS plus K times IR, when I substitute K times IR plus IS, okay, I get this value. So while I differential is this value, so I differential already greater than KIR plus IS, so relay will operate in this case. And for the 51 relay, if I divide now I ground fault divided by this C ratio, I get this current. Okay, so that over the CT ratio, the neutral CT, that gives me this. So this is much greater than the pickup of 0.2, so really easily will operate this. Now, if we go for 1 ohm, moderately grounding resistance, so I'll go for, I'll repeat the same thing for 10 ohm for high grounding resistance. I'll see how that affects. Now, because this all the impedance is in per unit, here all it's in per unit, so I'll convert this to per unit first. So 10 ohm is 10 ohm over Z base, give me the Z base already evaluated as Z base is V base square, which is 15.5 square divided by S base is 125 in this case. So I got 1.92, so that's converted to a per unit value. Now I use it here, 3 times Rn plus the sum of all the positive, negative, and zero sequence impedances. I got the fault current, zero positive, negative, zero currents, and from which 3 times I naught give me the fault current in per unit, and if you multiply by base current, I get the fault current in ampere. And now if I divide by CT ratio of the differential relay, which is 5,000 over 5, which is 1,000, give me this current. And if I divide this fault current by the neutral CT, uh, I got this current. Now, of course, if you compare now the differential relay operation, differential relay KIR plus IS becomes 0.6, and differential relay 0.84 is very close. You are in the verge of operation. Yeah, it will operate, but this is very close to this. While in overcurrent relay, still 41 much greater than 0.2. So it's easily will operate. So as you can see, if I have even goes higher than 10 ohm, like 20 ohm, the differential relay will not operate, while the overcurrent relay will operate for ground fault. So that's why we cannot rely totally on differential relay to detect all type of faults. And we need still an overcurrent relay to protect the generator winding. So there are other things that I have not completed. There are so many, there are other things that you have to take into consideration. And we said here that not all the generator winding will be protected when fault is very close uh, to the star bond. Normally, this type of protection, the ground overcurrent relay, although it is sensitive as compared to differential, but cannot detect more than, it cannot protect more than 95%. You left with 5% of the winding is unprotected. So there has to be other types of protection which detects the fault within this 5% left. And this is one topic that one of you also can present. This 100, we call it 100% winding protection. There are other methods using harmonics as a criteria to detect fault within the last 5% of the winding. Okay, and I will close this chapter at this point. Okay, stop recording. If you have any questions, you can